In this section, we will be talking about relations and functions. We will find that functions are a special type of relation, so we'll start with relations. A relation is a rule that relates two sets together. In other words, we have two sets of numbers, and we are pairing up numbers in the first set with numbers in the second set. You could also say it's a correspondence. To keep the two sets straight from each other, we call the first set the domain, and we usually think of it as a set of x values. And we call the second set the range, and we usually think of it as a set of y values. There are many ways to represent a relation. The most common ones are an equation, or a set of ordered pairs, or a graph, or a table, or a mapping. There are other ways, but these are the 5 that we will be focusing on. Let's begin by looking at an example. Here we have an equation, y equals 3x minus 6. Since it's an equation, it's relating two variables, that means it's relating two sets together, the set of x values and the set of y values. If you give me an x value, a number in the first set, then I can pair that up with a number in the second set. For example, and we can start to fill in a table. If you give me the x value of 0, then what's going to happen here? 3 times 0 minus 6 is going to be 0 minus 6, which is negative 6. And so we get a y value of negative 6, and that corresponds to the x value of 0. Let's fill in a few more values in this table. If we have an x value of 1, then putting that in here, we'll get 3 minus 6, or negative 3, for our y value. So the number 1 corresponds to the number negative 3. 1 in the first set is paired with negative 3 in the second set. I'm writing the first set in blue to represent the domain. I'm writing the second set in red to represent the range. And we could go on. We could say 2, that will give us 6 minus 6, which is 0. So 2 in the domain corresponds to 0 in the range. And we could pick any number that we like. We could do, for example, 1.5. Doesn't have to be a whole number. 1.5 is going to give us 4.5 minus 6. That's a negative 1.5 in the range. And so this is an example of an equation representing this relation. This is an example of a table representing this relation. And of course, this table is incomplete because there are an infinite number of x values and an infinite number of y values and an infinite number of ways to pair them up with this equation or with this relation. So in an example like this, the equation really is the better method of representation. The table can only give us an idea of what's going on. The equation can give us all of the pairings in the relation. A related way of looking at a relation, the related way to the table is a mapping. In a mapping, we are going to list our domain values on the left and our range values on the right. And then we would show the pairing or the correspondence by connecting them with an arrow. So this is what a mapping looks like. And it's common to encircle the domain and the range with these ovals. I don't know why, it's just what we do. You don't have to do that. But this is a mapping. So you see it's kind of similar to a table. And we'll get into more complicated mappings to see how there is actually a little bit of a difference between a table and a mapping. Another representation is a set of ordered pairs. And we can see that from the table quite easily. So we have our set braces, and each ordered pair is going to consist of an x value and a y value. And again, since it's infinite, we cannot represent all of them, unfortunately. But we can look and see the exact same pairs as that are in the table. 0, negative 6, 1, negative 3, 2, 0, and so on, and so on, and so on. And again, I've written them in blue and red to highlight where the domain numbers are and where the range numbers are. The domain numbers, when we list a set of ordered pairs, are always the numbers that occur as the first coordinate in every ordered pair. The second coordinate in every ordered pair gives us the range numbers. The final method by which we will represent this relation is graphically. If we want to graph this relation, well, we could look at some ordered pairs and plot them. Here is 0, negative 6, 1, negative 3, 2, 0, and because this is a linear equation, we can draw the line through all of these. An alternate method would be to consider that this is slope-intercept form. This negative 6 tells us y-intercept is 0, negative 6. And this 3 tells us the slope is 3. So as we go to the right 3, we're going to go up. As we go to the right by 1, we're going to go up by 3 each time. And so we're going to get a line that looks something like this. Of course, it's hard to use a straight edge on a whiteboard, but it'll have to do. And so there's a graphical representation of our relation. And I've drawn the x-axis in blue and the y-axis in red to highlight the fact that, again, the x values are the domain values and the y values are the range values. So whereas before with a table or a mapping or a set of ordered pairs, it was impossible to list all of them, here we see a good representation of the infinite pairings in this relation, because any point that we pick anywhere on this line is going to give us one of the pairings, one of the correspondences. And so we can see by looking at this what the domain and the range are. Notice, the x-axis, which gives us the domain values, is the left to right axis. So by thinking about all the possible left to right values that this line can assume, we can get the domain. Looking at this arrow, that arrow tells us it's going to continue infinitely in this direction. Well, this direction is down and to the left. So it's going to continue infinitely down and infinitely left. And this arrow tells us it's going to continue infinitely up and right. So in the left-right direction, it's going to go infinitely left, and it's going to go infinitely right. And it's a line. It's not broken. There's nothing missed. So the domain is everything, all real numbers, from negative infinity to infinity. What about the range? Well, again, it goes infinitely down and infinitely up. Nothing is missed in the middle. And so the range for this particular relation is also everything, all real numbers, negative infinity to infinity. We'll see more examples that have different domains and ranges than this. And one more thing to notice about this example is that anytime I'm given a domain value, the rule will give me one range value. Any x I put in here, I will multiply by 3 and subtract 6. That will give me exactly one y value. And that makes this a special type of relation. It's called a function. Now, before we specifically define what a function is, we're going to look at an example of a relation that is not a function so that we can see the difference. Here's another example. And this example is going to end up not having the same property as the first example. It is given by the equation x equals the absolute value of y. Let's get an idea of what's going on by drawing a mapping. If I have an x value of 0, what y value can I have that will match up with that? Well, there's only one. 0. Okay. Now, on the other hand, if I have an x value of 1, what will that match up to? What number can I take the absolute value of to get 1? Well, I can do 1, of course, but I can also do negative 1. So the number 1 in the domain is paired with both 1 and negative 1 in the range. This is the reason that this relation is not a function. It is because in this example we have a number in the domain being paired with multiple numbers in the range, whereas in example 1, each number in the domain was paired with exactly one number in the range. Another thing to notice about this example is that the domain is not all real numbers. Notice if I try to pair a negative 1 in the domain with something in the range, it's not going to work because there is no number I can take the absolute value of to get a negative 1 here. So it doesn't get paired with anything. It cannot be in the domain. So this tells us that the domain here is actually going to be only non-negative numbers. The range can still be anything because I can take the absolute value of any number. So what exactly is a function? What is the difference between the first example and the second example? Well, a function is a kind of relation that has the property that it assigns exactly one range value to each domain value. In example 1, we saw that to be the case. Given an x, I put it into 3x minus 6, and that gives me one y value. In example 2, that was not the case. Given an x, there were typically two values that I could take the absolute value of to get that x value.